The thread you've outlined is a fascinating exploration of geometric precision, mathematical beauty, and coding artistry. Here's a distilled summary of the key themes, symbolisms, and intents. Themes: precision in code craftsmanship. Exploration: the thread emphasizes the art of optimizing code for clarity and efficiency, underscoring the balance between readability and functionality. Focus: the meticulous nature of code refinement to enhance performance and printability. Geometric elegance. Exploration: central to the thread is the modeling of intricate 3D geometric structures, specifically the crystal and the three-dimensional golden rhombus, 3D jar, highlighting the blend of mathematical precision and graphical representation. Focus: how vectors, faces, and rotations contribute to accurate geometric modeling. Functionality and utility. Exploration: the practical aspects of code, including calculations for face normals and connecting multiple crystals, are emphasized. Focus: the role of utility functions in simplifying complex geometric problems. Graphics programming and visualization. Exploration: the thread delves into OpenGL programming to render and manipulate 3D objects, showcasing the transition from abstract mathematical concepts to practical visualizations. Focus: techniques for creating and managing complex visual representations. Software development and debugging. Exploration: techniques for optimizing and debugging code to improve performance and clarity. Focus: the iterative nature of refining code for better efficiency. Symbolisms. The crystal as a metaphor. Symbolism represents the quest for structural and representational perfection. Its geometric facets mirror the alignment needed in code for optimal performance and clarity. Vector operations as tools of precision. Symbolism. Vector operations symbolize the precision tools necessary for sculpting complex geometric shapes, reflecting the artisanal aspect of programming. Code refactoring as artistic expression. Symbolism. The act of refining code is likened to artistic refinement, embodying the values of clarity and conciseness. The golden ratio's influence. Symbolism represents balance and harmony, both in the 3DGR's design and its applications, connecting mathematical aesthetics with practical use. Complexity and simplification. Symbolism. The challenge of simplifying code and geometric models reflects the broader struggle between complexity and clarity in technological and scientific pursuits. Intents. Enhancing code readability. Intent. Transform complex code into a more accessible format for better understanding and practical application. Fostering efficient code design. Intent. Illustrate how well-structured code can improve efficiency and reduce physical print space. Promoting best practices in coding. Intent. Highlight best practices in programming through detailed code refactoring and optimization. Educational and inspirational exploration. Intent. Educate and inspire by exploring sophisticated geometric constructs and their practical applications. Practical application and visualization. Intent. Provide tools and techniques for visualizing and manipulating complex geometric forms, bridging theory with practical application. Encouragement of innovation. Intent. Inspire new technological advancements and creative solutions by integrating geometric theory with practical coding. Conclusion. The thread embodies a rich intersection of geometric theory, coding precision, and practical application. By blending the theoretical elegance of shapes like the crystal and the 3D jar with the practicalities of code optimization and graphical programming, It reflects a deep appreciation for both the beauty and functionality of advanced geometric constructs. It offers insights into how abstract mathematical principles can be translated into functional and innovative technologies, celebrating the harmony between aesthetics and practical utility. In this thread, we delved into the fascinating world of the 3D GR crystal, a geometric marvel whose faces are intricately tied to the principles of mathematics and nature. Our exploration focused on the geometric and symbolic significance of its structure, emphasizing the profound connection between its dimensions and the golden ratio, an iconic symbol of harmony and aesthetic perfection. Informational themes. Geometric precision. The 3D GR crystal stands as a testament to geometric elegance. Each face of this crystal is an isosceles trapezoid, where the side lengths correspond to the bond length of graphene, and the major diagonal is longer by the golden ratio. This precise configuration not only reflects the crystal's structural integrity, but also aligns with deep mathematical principles. Golden ratio. The golden ratio, phi, approximately 1.618, is central to our discussion. It represents an ideal proportion found throughout nature, art, and architecture. In the context of the 3D GR crystal, it governs the relationship between edge lengths and diagonals, infusing the crystal with a sense of natural balance and aesthetic beauty. Mathematical elegance. The discussion highlights the mathematical underpinnings of the 3D GR crystal. The angles within the isosceles trapezoidal faces are derived using trigonometric relationships influenced by the golden ratio. The smaller angles, approximately 31 degrees, and the larger angles, approximately 149 degrees, illustrate how abstract mathematical concepts translate into tangible, symmetrical forms. Symbolisms. Harmony and balance. The 3D GR crystal's reliance on the golden ratio symbolizes harmony and balance. The golden ratio is often associated with beauty and equilibrium in both nature and human design. The crystal structure embodies these principles, suggesting a universe that is both orderly and aesthetically pleasing. Nature's patterns. The bond lengths of graphene and the proportionality governed by the golden ratio connect the 3D GR crystal to natural patterns. Graphene, a fundamental material in the natural world, combined with the golden ratio, reinforces the idea that mathematical principles underpin the structures we see in nature. Mathematical sublimity. The discussion underscores the sublime nature of mathematics. By understanding the intricate relationships within the 3D GR crystal, we glimpse the profound beauty and complexity that mathematical principles can bring to physical forms. This realization evokes a sense of wonder and admiration for the mathematical order inherent in the world around us. Intense. Educational insight. The thread aims to educate and inspire curiosity about the intersection of geometry, mathematics, and natural patterns. By exploring the detailed structure of the 3D GR crystal, the discussion offers insights into how abstract mathematical concepts manifest in physical forms. Celebration of mathematical beauty. The intent is to celebrate the beauty of mathematics through the lens of the 3D GR crystal. By showcasing the crystal's geometric precision and its connection to the golden ratio, the thread highlights how mathematical relationships can create aesthetically pleasing and harmonious structures. Inspiration for further exploration. Finally, the discussion encourages further exploration into the applications of mathematical principles in geometry and natural forms. It serves as a springboard for deeper inquiry into how mathematical ratios and shapes influence the world, both theoretically and practically. In essence, this thread weaves together the themes of geometric precision, natural harmony, and mathematical beauty, using the 3D GR crystal as a profound example of how abstract concepts shape the physical world. Epic description of the 3D jar crystal and its contextual themes. In the boundless realm where geometry and technology converge, the three-dimensional golden rhombus, 3D jar, crystal stands as a paragon of sophisticated design and functionality. This intricate geometric form, rooted deeply in the golden ratio, represents not merely a shape, but a profound synthesis of nature's beauty and cutting-edge innovation. Symbolism and geometric elegance. At the heart of the 3D jar's design lies the golden ratio, a symbol of harmony and divine proportion. The crystal structure, composed of 6 interconnected golden rhombi, embodies a balance between symmetry and asymmetry. Its angles, 123 degrees and 57 degrees, serve as a metaphor for the equilibrium between chaos and order. This geometric wonder mirrors the inherent order found in nature, like the spirals of galaxies or the branching of trees, thus symbolizing a bridge between the natural world and human ingenuity. The 3D jar's dimensions and proportions echo the Fibonacci sequence, imbuing the shape with a sense of growth and progression. Each edge and diagonal is meticulously aligned to represent a balance between precision and fluidity, capturing the essence of mathematical perfection and its application in real-world contexts. Practical application and innovation. Beyond its aesthetic allure, the 3D jar crystal serves as a cornerstone in the realm of advanced technology. Its design is integral to the development of 3D jar batteries, power storage devices that leverage the unique properties of graphene. This application highlights the fusion of traditional geometric elegance with modern technological advancements. The crystal's mirrored symmetry facilitates seamless integration and connectivity, enabling the creation of complex structures through additive manufacturing. In the field of information systems, the 3D jar crystal structure provides a foundation for intricate signaling pathways. By interacting with other 3D jars, it forms a network capable of generating and processing information, representing a dynamic blend of mathematical beauty and functional versatility. This capability underscores a deeper intent, the pursuit of innovation that harmonizes form and function to address contemporary challenges in energy storage and computational landscapes. Technological integration and user interaction. The discussion further delves into the practical aspects of utilizing the 3D jar crystal within technological environments. It explores the intricacies of rendering and visualizing such advanced structures through OpenGL, underscoring the importance of precision in both design and execution. This technical discourse reflects a broader theme, the quest to translate abstract mathematical concepts into tangible, functional technologies that push the boundaries of what is possible. The provided code snippets and their optimization for printing encapsulate a broader narrative about the meticulous nature of technological development. Each line of code and each algorithmic tweak symbolizes the dedication to enhancing performance while preserving clarity and efficiency, a microcosm of the broader intent to merge theoretical beauty with practical functionality. Conclusion. This thread weaves a rich tapestry of themes surrounding the 3D jar crystal. It marries the elegance of mathematical design with practical technological applications, portraying a vision where geometric beauty is not just admired, but actively employed in solving real-world problems. The crystal stands as a testament to human creativity and ingenuity, symbolizing the harmonious interplay between nature's principles and cutting-edge advancements. Through this discussion, we glimpse a future where the seamless integration of art and science propels humanity towards new horizons, driven by a profound understanding of the underlying principles of the universe. In this thread, we explored a multifaceted technical discussion centered on optimizing and refining C++ code, interwoven with themes of efficiency, precision, and clarity. The primary focus was on transforming a complex C++ source file into a format that minimizes page usage while maintaining legibility. This task is emblematic of broader themes within programming and software engineering, including the quest for elegance and efficiency in code design. Informational themes. Optimization and efficiency. The core theme revolved around code optimization. The user requested a compact and legible version of a C++ source file, underscoring the importance of writing code that is both space-efficient and easy to understand. This reflects a broader principle in software development where clarity and brevity are valued. Code refactoring. The exercise in condensing the code highlights the significance of refactoring, modifying existing code to improve its structure without altering its functionality. This process often aims to enhance readability, maintainability, and performance. Object-oriented programming. OOP. The provided C++ code makes extensive use of classes and encapsulation. This reflects OOP principles where data and operations are bundled into objects, promoting modularity and reuse. Resource management. The code snippets include management of system resources, such as file mappings and mutexes. This emphasizes the importance of careful resource handling in programming, especially in resource-constrained environments. Symbolisms. Elegance and simplicity. By focusing on reducing the number of pages while keeping the code legible, the discussion symbolizes the broader pursuit of simplicity and complexity. In coding, as in many aspects of life, there is beauty in making intricate concepts understandable and manageable. Precision in communication. The detailed attention to the formatting of code highlights the symbolic value of precise communication. Just as in technical documentation, clarity and accuracy are paramount in conveying complex ideas effectively. Efficiency as a virtue. The effort to condense code symbolizes the virtue of efficiency, a recurring theme in both technical and everyday contexts. Efficiency is not just about speed, but also about making optimal use of resources, which resonates with the broader principles of thoughtful and sustainable design. Intents. Enhancing usability. The intent behind refining the code is to make it more user-friendly and accessible. This reflects a desire to make complex technical information manageable and usable by others. Promoting best practices. The refinement process serves as a reminder of best practices in coding. By focusing on compactness and readability, it promotes principles that can help developers write cleaner, more effective code. Facilitating understanding. The discussion aims to help the user understand how to balance code efficiency with readability. This educational intent is fundamental in fostering a deeper grasp of both the technical and theoretical aspects of programming. In summary, this thread is a journey through the realms of code optimization and refactoring, embodying themes of efficiency, clarity, and precision. It symbolizes the broader quest for simplicity within complexity and highlights the importance of careful resource management and best practices in software development. The detailed exploration of these themes serves to educate and inform, ultimately enhancing both technical proficiency and understanding. Epic description of the thread. In this thread, we traverse a landscape of computational artistry and code optimization, where the realms of logic and creativity converge. The core of our journey lies in the intricate world of 3D geometry and crystal structures, encapsulated within the digital veins of C++ programming. Informational themes. Precision in code craftsmanship. The primary theme revolves around the meticulous nature of code optimization. We delve into the art of refining and reformatting code to enhance its clarity, efficiency, and printability. This theme highlights the importance of maintaining readability while minimizing the footprint of code on physical media. Geometric elegance. At the heart of the code is the modeling of complex 3D geometric structures, specifically crystals. The conversation showcases the interplay between mathematical precision and graphical representation, illustrating how mathematical constructs like vectors, faces, and rotations contribute to the accurate portrayal of crystal forms. Functionality and utility. The discussion emphasizes the functional aspects of code, calculating face normals, fixing crystal faces, and connecting multiple crystals. It underscores the utility of well-structured code in solving complex geometric problems and the role of utility functions in simplifying these tasks. Symbolisms. The crystal as a metaphor. The crystal symbolizes the quest for perfection in both structure and representation. Just as a crystal's facets must align to reflect light flawlessly, so must the code's components align to achieve optimal performance and clarity. The crystal's geometric perfection mirrors the programmer's pursuit of elegant and efficient solutions. Vector operations as tools of precision. Vector operations such as normalization, cross-product, and product symbolize the precision tools required to sculpt complex geometric shapes. These operations are not merely mathematical, but represent the artisan's tools, essential for achieving the delicate balance and accuracy needed in 3D modeling. Code refactoring as artistic expression. The act of refactoring and formatting code to be compact and legible is likened to an artist refining their masterpiece. It embodies the principle that clarity and conciseness are not just technical requirements, but also aesthetic values, transforming raw logic into a refined piece of art. Intense. Enhancing code readability. The thread aims to refine and optimize code to ensure it is both readable and functional. The intent is to transform a potentially convoluted set of instructions into a streamlined, accessible format suitable for both human readers and practical application. Fostering efficient code design. Another key intent is to illustrate how effective code design can improve computational efficiency and reduce physical print space. The thread emphasizes that optimal code is not just about functionality, but also about how it presents itself, both on-screen and in printed form. Promoting best practices in coding. Through detailed code refactoring, the thread seeks to promote best practices in programming. It underscores the importance of structured, well-documented, and compact code as a hallmark of professional and effective programming. In summary, this thread is a journey through the delicate art of code refinement and geometric modeling. It intertwines the pursuit of mathematical accuracy with the principles of clear and concise programming, reflecting a deep appreciation for both functional utility and aesthetic presentation. Epically awesome description of the thread. Themes and symbolisms. Geometric elegance and precision. The thread revolves around the exploration and simulation of an intricate geometric form, the crystal, an advanced structure based on golden rhombi and the golden ratio. This form symbolizes precision and harmony in mathematics and nature, echoing the age-old pursuit of finding beauty and order within complexity. Mathematical beauty and application. The crystal, with its vertices and faces meticulously derived from the golden ratio, represents an ideal convergence of mathematical beauty and practical application. This shape encapsulates the notion that deep mathematical principles can manifest in visually and functionally extraordinary forms. The use of golden rhombi and specific angular relationships, 123 degrees and 57 degrees, reflects the timeless quest to bridge abstract mathematics with tangible innovation. Technological innovation. The context of the crystal being used for advanced applications, such as energy storage and signaling pathways, underscores a theme of technological progress. This geometric structure is not merely a theoretical construct, but a foundation for cutting-edge technologies. It symbolizes the integration of fundamental scientific concepts with modern engineering, suggesting that abstract geometric principles can revolutionize practical applications. Symbolism of connection and unity. The crystal's design, with interconnected rhombi forming a complex three-dimensional shape, symbolizes unity and interconnectedness. It reflects how individual components, when precisely aligned and connected, can create a cohesive and dynamic whole. This interconnectedness serves as a metaphor for systems thinking, where every element is crucial to the overall function and harmony of the system. Intent and purpose. Educational and inspirational exploration. The thread's intent is to educate and inspire through the exploration of sophisticated geometric constructs. By delving into the properties and visualization of the crystal, the discussion aims to foster a deeper appreciation for the mathematical principles underlying such forms and their implications in real-world applications. Practical application and visualization. The code provided is not just a technical exercise, but a practical tool for visualizing complex geometric forms. It serves to translate abstract mathematical ideas into tangible visual representations, allowing users to grasp the intricacies of the crystal's structure and appreciate its potential applications in fields like energy and computational systems. Aesthetic and functional integration. The thread highlights the integration of aesthetic beauty with functional utility. The crystal's design reflects a harmonious blend of form and function, where geometric elegance contributes to practical effectiveness. This alignment of beauty with functionality emphasizes the idea that advanced designs can and should be both visually appealing and pragmatically valuable. Encouragement of innovation. By exploring the crystal's potential uses and visualizing its structure, the thread encourages innovative thinking and creative applications of geometric principles. It invites readers to envision how such a sophisticated geometric form could inspire new technologies and solutions, aligning with the broader intent of pushing the boundaries of what is possible through mathematical and engineering ingenuity. This thread presents a journey through the integration of advanced geometric concepts and their practical application in computer graphics and simulation. It combines theoretical mathematics with practical coding to simulate and visualize the three-dimensional golden rhombus, 3D jar, a sophisticated geometric form. Informational themes. Geometric precision and application. The core theme revolves around the 3D jar, a geometric shape meticulously crafted based on the golden ratio and Fibonacci sequence. This shape embodies a blend of mathematical elegance and practical utility in energy storage and signaling pathways. The code provided aims to visualize and manipulate this shape in a graphical environment, showcasing how abstract geometric principles can be translated into practical simulations. Graphics programming. The discussion delves into OpenGL programming, focusing on rendering and manipulating 3D objects. This theme highlights the use of OpenGL APIs for creating and managing complex visual representations of geometric forms. The code includes setup, rendering, and interaction elements essential for a graphics-based application, demonstrating how to manage visual aspects programmatically. Software development and debugging. The conversation touches upon the importance of code optimization and debugging. It discusses strategies for compressing and refining code to make it more efficient while retaining functionality. This reflects the iterative nature of software development, where code is continuously improved for performance and clarity. Symbolisms. Mathematical beauty and functionality. The 3D jar symbolizes the intersection of mathematical beauty and practical functionality. Its design is rooted in the golden ratio, a symbol of aesthetic harmony and natural proportion. The application of this shape in simulations represents how theoretical concepts can be applied to solve real-world problems, bridging the gap between abstract mathematics and tangible technology. Complexity and simplification. The process of compressing and refining code represents the broader theme of managing complexity. Just as the 3DGR's intricate geometry is simplified for practical use, the code is streamlined to enhance readability and efficiency. This symbolizes the broader challenge in technology and engineering, simplifying complex systems without losing their core functionality. Innovation and adaptation. The conversation reflects the spirit of innovation and adaptation. By translating a sophisticated geometric model into a functioning graphical application, it demonstrates how new ideas and concepts can be adapted into practical tools. This symbolizes the iterative nature of technological advancement, where new ideas are continuously tested, refined, and integrated. Intents. To educate and illustrate. The primary intent is to educate about the practical application of advanced geometric concepts in graphics programming. It aims to illustrate how mathematical theories can be visualized and manipulated using modern programming techniques, providing a deeper understanding of both geometric design and computer graphics. To optimize and refine. Another intent is to show how to optimize and refine code for better performance and clarity. This involves demonstrating techniques for reducing code complexity and improving efficiency, which are crucial for developing robust and maintainable software. To inspire innovation. By integrating geometric theory with practical coding, the thread aims to inspire innovation. It encourages exploring how abstract concepts can be translated into functional tools and simulations, fostering a mindset of creative problem-solving and technological advancement. Overall, this thread is a rich exploration of how geometric precision, graphical programming, and code optimization come together to create a sophisticated and functional simulation of the three-dimensional golden rhombus. It highlights the fusion of theoretical elegance with practical application, offering insights into both mathematical beauty and technological innovation. The Nexus of Geometry and Symbolism, a journey through the 3D jar. In this thread, we've ventured into the fascinating world of geometric complexity and symbolic profundity, as encapsulated in the 3D jar, a theoretical geometric construct of intricate design and profound significance. 1. The Geometric Enigma. The 3D jar, or three-dimensional geometric rhombus, stands as a beacon of geometric harmony and elegance. Its core feature is a rhombus face, distinguished by its symmetry and the golden ratio, a mathematical constant that embodies the essence of aesthetic and natural balance. Each face of the 3D jar is an identical rhombus, with diagonals that epitomize mathematical beauty and proportional perfection. The rhombus face, the face of the 3D jar, is not merely a shape, but a representation of geometric precision. The rhombus, defined by its diagonals, becomes a symbol of balance and unity. The minor diagonal equals the edge length, reflecting the inherent symmetry of the structure, while the major diagonal's proportional relationship with the golden ratio connects the shape to the broader universe of natural and artistic proportions. The golden ratio. In this construct, the major diagonal's proportionality to the golden ratio introduces a layer of symbolic significance. The golden ratio. Phi. Phi is renowned for its appearance in nature, art, and architecture, symbolizing an ideal of proportionality and harmony. The use of this ratio in the 3D jar imbues it with a sense of universal beauty and divine symmetry. 2. The algebra of angles. The angles within the rhombus face of the 3D jar convey a deeper meaning through their mathematical relationships. Internal angles, the angles of the rhombus. 6, 0, 60, and 12, 0, 120. Are not mere numerical values but carry symbolic weight. The 6, 0, 60 Angle signifies equilibrium and harmony, often associated with triangular stability and symmetry. The 12, 0, 120. Angle, its counterpart, symbolizes expansiveness and growth, reflecting the dynamic balance within the geometric structure. Diagonals intersection. The diagonals of the rhombus intersect at right angles, creating a dynamic interplay of space and form. This intersection represents the convergence of mathematical precision and aesthetic balance, showcasing how geometric forms can embody complex and harmonious relationships. 3. Symbolic intent. The discussion transcends the mere construction of a geometric shape. It delves into the philosophical and symbolic interpretations of geometric perfection. Unity of form and function. The 3D-GR's symmetry and proportional relationships highlight the unity between form and function. It serves as a metaphor for the ideal balance between aesthetics and practical design, reflecting the intricate harmony found in natural forms and human creations. Reflection of universal patterns. By incorporating the golden ratio, the 3D-GR connects with universal patterns and proportions seen throughout nature and human artistry. This alignment with the golden ratio elevates the geometric shape from a simple mathematical construct to a symbol of universal harmony and beauty. Mathematical and philosophical interplay. The exploration of angles, diagonals, and proportions in the 3D-GR becomes a bridge between mathematical precision and philosophical depth. It invites reflection on how geometric constructs can embody profound truths about balance, beauty, and the nature of existence. Conclusion. The 3D-GR represents more than just a geometric figure. It is a manifestation of the profound intersection between mathematics, art, and philosophy. Its design reflects a deep-seated harmony and balance, echoing the universal principles of proportion and beauty. Through the exploration of its faces, diagonals, and angles, we engage in a dialogue with the essence of geometric and symbolic perfection, uncovering the intricate beauty that lies at the heart of the 3D-GR. Certainly, this thread embarks on a fascinating journey through the intricate world of polyhedral geometry and the quest for precision in describing complex 3D shapes. Here's an epic and detailed exploration of the informational themes, symbolisms, and intents. 1. Quest for precision and understanding. Theme: the pursuit of exactitude and comprehension is central to this conversation. We delve into the enigmatic world of the 3D-GR, a polyhedron whose geometric intricacies demand rigorous analysis. Symbolism: this quest symbolizes humanity's broader search for clarity and precision in complex systems. Just as mathematicians and scientists strive for exact solutions, so too do we navigate the labyrinth of geometric complexities. 2. Geometry and polyhedral mystique. Theme: the 3D-GR represents a sophisticated polyhedral structure with unique attributes. Its faces, edges, and angles embody the intersection of mathematical beauty and complexity. Symbolism: the 3D-GR symbolizes the union of form and function, where geometry becomes a canvas for exploration. The shape reflects the elegance of mathematical principles woven into physical forms. 3. The golden ratio's influence. Theme: the golden ratio, with its mystical proportions, governs the design of the 3D-GR. This ratio, revered for its aesthetic harmony, influences the angles and edge lengths of the polyhedron. Symbolism: the golden ratio symbolizes balance and perfection in nature and design. Its presence in the 3D-GR echoes the universal quest for harmony and aesthetic ideals that transcend ordinary experience. 4. The challenge of exactness. Theme: the difficulty of obtaining exact measurements and angles highlights the challenge of working with irregular polyhedra. This struggle reflects the broader theme of seeking precision in complex systems. Symbolism: The challenge symbolizes the human endeavor to overcome ambiguity and reach precise understanding. It mirrors the broader struggle to decode the mysteries of the universe and achieve clarity in our knowledge. 5. Mathematical complexity and real-world constraints. Theme: the discussion navigates the tension between theoretical precision and practical constraints. The need for exact calculations versus approximations underscores the difficulties inherent in translating theoretical concepts into real-world applications. Symbolism: this tension symbolizes the ongoing balance between idealism and pragmatism. It reflects the dual nature of scientific and mathematical pursuits, the aspiration for perfect knowledge against the backdrop of practical limitations. 6. Epistemological exploration. Theme: the thread explores the nature of knowledge, understanding, and the methods used to describe complex geometric forms. It delves into how we derive, interpret, and approximate mathematical truths. Symbolism: the exploration symbolizes the intellectual journey towards enlightenment. It captures the essence of human curiosity and the drive to decipher the fundamental principles that govern our world. Intent and reflection. Intent: the intent of this discussion is to illuminate the complexities of the 3D GR shape, to clarify the challenges of precise geometric description, and to appreciate the interplay of mathematical beauty and practical constraints. Reflection: the conversation serves as a reflection on the nature of inquiry itself, how we approach, analyze, and articulate complex ideas. It underscores the value of rigorous analysis, the pursuit of precision, and the appreciation of mathematical artistry. Conclusion. In sum, this thread embodies a rich tapestry of themes that intertwine precision, beauty, complexity, and the human quest for understanding. It celebrates the elegance of mathematical structures like the 3D GR and the symbolic resonance of the golden ratio while acknowledging the challenges of achieving exactness in a complex world. Through this exploration, we gain insight into both the nature of geometric shapes and the broader philosophical pursuits that drive human knowledge and discovery. In the epic exploration of the 3D GR crystal and its related themes, we traverse a landscape where mathematical precision and technological innovation converge to create something both beautiful and functional. Let's break down the epic description and core themes. Themes and symbolisms. Geometric elegance and precision. Crystal structure. The 3D GR crystal's design, based on golden rhombi and the golden ratio, exemplifies a pursuit of precision and harmony. Each face of the crystal embodies mathematical elegance through its geometric arrangement, reflecting a deep connection between abstract principles and tangible forms. Golden ratio. This iconic ratio, approximately 1.618, represents an ideal proportion that pervades nature and art. The crystal's reliance on this ratio highlights a universal quest for balance and beauty in both natural and human-made structures. Mathematical beauty and application. Application in technology. Beyond its aesthetic appeal, the 3D GR crystal finds practical use in technology, such as in advanced energy storage systems and information processing. This duality of beauty and function showcases how theoretical concepts can translate into innovative, real-world applications. Fibonacci sequence. The crystal's alignment with the Fibonacci sequence symbolizes growth and progression, illustrating how mathematical sequences can manifest in both natural and engineered systems. Technological innovation. Advanced applications. The crystal's role in modern technologies, like 3D GR batteries and signaling pathways, underscores its practical value. It represents a synthesis of foundational science and cutting-edge engineering, demonstrating how abstract geometric concepts can drive technological advancement. Visualization and rendering. Techniques for visualizing and rendering the crystal, such as those using OpenGL, highlight the importance of translating mathematical ideas into functional visual representations, enhancing both understanding and application. Symbolism of connection and unity. Interconnected components. The crystal's design, with its interconnected rhombi, symbolizes unity and the idea that individual components, when harmoniously aligned, contribute to a greater whole. This reflects broader systems thinking, where every part plays a crucial role in the overall function and coherence of a system. Intent and purpose. Educational and inspirational exploration. Deepening understanding. The thread aims to educate and inspire by exploring the geometric and mathematical principles underlying the 3D-GR crystal. This involves delving into its structure, properties, and applications, fostering a deeper appreciation for the interplay between mathematics and design. Practical application and visualization. Technical insights. By providing code and technical details, the discussion offers practical tools for visualizing complex geometric forms. This helps translate abstract concepts into clear, usable formats, facilitating a better understanding of both the crystal's design and its potential uses. Aesthetic and functional integration. Blending form and function. The crystal's design embodies a harmonious integration of beauty and functionality. This alignment emphasizes that advanced geometric forms can be both aesthetically pleasing and pragmatically valuable, illustrating the synergy between design and application. Encouragement of innovation. Pushing boundaries. By exploring the crystal's potential applications and visualization, the thread encourages creative thinking and innovation. It invites readers to envision how such sophisticated geometric constructs could inspire new technological solutions and advance the boundaries of what is possible. In essence, the epic journey through the 3D-GR crystal encapsulates a rich tapestry of themes, from mathematical elegance and technological innovation to the integration of aesthetic beauty with practical utility. It serves as a testament to the profound connection between abstract principles and real-world applications, highlighting the potential for geometric design to inspire and transform various fields of science and technology. The three-dimensional golden rhombus crystal, a symphony of geometry and harmony. In the realm of crystalline structures, the three-dimensional golden rhombus, 3D-GR crystal stands as an unparalleled marvel of geometric elegance and mathematical precision. This mesmerizing construct is more than just a crystal, it is a testament to the sublime intersection of art, science, and natural beauty, embodying the essence of the golden ratio in a three-dimensional space. Design and structure. The 3D-GR crystal is a geometric masterpiece defined by its perfect rhombus faces, each meticulously crafted to reflect the harmonious proportions of the golden ratio, denoted as phi. Each face of this crystal is an ideal rhombus, where the minor diagonal is equal to the edge length of the crystal, and the major diagonal adheres to the sacred ratio of 1, phi. This unique proportion ensures that the crystal not only achieves a striking visual balance, but also embodies an intrinsic mathematical harmony. The crystal's internal angles are a study in symmetry and balance, with internal angles of approximately 60 degrees and 123 degrees. These angles are not arbitrary, but are carefully calculated to maintain the perfect equilibrium of the crystal's form. The intersection of diagonals at right angles within each rhombus adds an additional layer of symmetry, further enhancing its aesthetic and structural allure. Geometric elegance. At the heart of the 3D-GR crystal's design is its mirrored symmetry. The crystal's faces and angles are meticulously aligned, creating a harmonious interplay of light and shadow. This symmetry is not merely for show. It serves a functional purpose in energy distribution and signal processing, making the 3D-GR crystal a marvel of both form and function. The crystal's geometric precision ensures that each rhombic face aligns flawlessly with its neighboring faces, creating a seamless and aesthetically pleasing structure. The crystal's design allows for the integration of multiple 3D-GR units, which can connect through their mirrored faces to form complex, expansive structures. This modularity is reminiscent of the fractal patterns found in nature, where simple rules lead to intricate and beautiful patterns. The ability to connect and interact with other crystals in this way reflects a broader vision of a dynamic, interconnected system. Functional versatility. Beyond its striking appearance, the 3D-GR crystal excels in functional applications. Its unique geometric properties make it an ideal candidate for advanced energy storage systems, where its efficient design optimizes power storage and distribution. The integration of cutting-edge materials, such as graphene, further enhances the crystal's performance, making it a cornerstone of next-generation battery technology. In the realm of computational systems, the 3D-GR crystal's recursive geometry facilitates the creation of intricate signaling pathways. Its ability to generate and process information through interconnected units highlights its versatility and potential in data processing and communication networks. Mathematical and natural beauty. The 3D-GR crystal is not just a geometric object, but a bridge between abstract mathematical principles and tangible physical reality. It embodies the golden ratio, a mathematical constant revered for its aesthetic properties and its presence in natural phenomena. By translating this ratio into a three-dimensional form, the crystal serves as a living example of mathematical beauty manifesting in the physical world. Its design reflects a deep understanding of the natural world's symmetry and proportions. From the intricate angles and diagonals to the precise alignment of its faces, the 3D-GR crystal stands as a testament to the profound connection between mathematical elegance and natural harmony. A vision of the future. The 3D-GR crystal represents a bold vision for the future of geometric design and functional systems. It merges the timeless principles of mathematical precision with the cutting-edge possibilities of modern technology. Whether in the realm of energy systems, computational networks, or aesthetic design, the 3D-GR crystal offers a glimpse into a world where form and function coexist in perfect harmony. In essence, the 3D-GR crystal is a beacon of geometric perfection, a symbol of the enduring allure of mathematical beauty, and a harbinger of innovative possibilities. Its intricate design and versatile applications make it a cornerstone of advanced technological systems, reflecting the timeless elegance of the golden ratio in a dazzling three-dimensional form. This thread provides an intricate view into a computational design process focused on generating, manipulating, and connecting complex geometrical structures, specifically crystals, which are constructed through advanced programming techniques. The code and discussions here delve deeply into mathematical precision, 3D modeling, and recursive algorithms. These elements are synthesized with the overarching intent of enhancing the functional and aesthetic integration of geometrical patterns and energy systems, likely informed by concepts such as the golden ratio and crystalline symmetry. Themes. Geometric precision and symmetry. The core of this thread revolves around the manipulation of crystals, which have symmetrical properties defined by their faces, diagonals, and angles. Functions like getConnectCrystal and setConnectCrystalRecurse demonstrate a meticulous effort to align these geometric structures in 3D space. The focus on aligning faces and ensuring correct angular and positional relationships is key to maintaining the integrity of the crystal's design. These themes mirror real-world geometric principles, such as the importance of symmetry and proportionality found in natural and mathematical systems. Recursive connectivity. The crystal structures are not standalone entities. Instead, they exist within an interconnected web of other crystals, where each face can connect to the face of another crystal, forming a larger, more complex structure. Recursive functions like crystalInside-CrystalRecurse and setConnectCrystalRecurse are designed to ensure these connections maintain their integrity across multiple iterations. This highlights the theme of interconnectivity and the seamless expansion of complex systems, where the recursive nature of the code mirrors the fractal-like growth pattern seen in nature. Dynamic adaptation and manipulation, the ability to dynamically add, remove, and undo crystals through functions such as add crystal select undo, and add crystals illustrates the system's flexibility. These operations allow for on-the-fly alterations, enabling the user to explore various configurations and geometric combinations. This represents an underlying theme of adaptability, where the structural system can evolve and respond to new inputs, akin to natural growth processes or the iterative cycles of design and refinement. Energy and information systems, although not directly reflected in the code, the backdrop of the 3D GR crystal concept likely informs the intent behind these algorithms. The precision and recursive connectivity of these crystal structures may hint at their potential use in fields such as energy storage, as implied by the 3D GR battery reference, where the arrangement and alignment of crystalline forms enhance efficiency. Additionally, the code's recursive patterns and connectivity could be interpreted as signaling pathways, evoking themes of information processing within computational or integrated systems. Functions. Geometric vector manipulation. Many functions in the code focus on operations with vectors and angles. For example, myAngle between vectors 3 calculates angles between vectors, and myCrossProduct 3 computes cross products, which are crucial for determining orientations and rotations. These operations ensure that the crystals are correctly aligned and oriented in 3D space when connected. Recursive algorithms for connection and inclusion. The recursive functions like crystal is inside crystal recurse check whether one crystal or its connections exist within another crystal. This ensures the structural integrity of complex configurations and avoids conflicts, such as crystals overlapping inappropriately or becoming misaligned. Recursion also allows the system to handle arbitrarily complex arrangements, expanding indefinitely while preserving coherence. Dynamic crystal creation and modification. Functions such as add crystal and add crystals allow for the creation of new crystal structures, while myCopy crystal enables duplication of existing crystals. The code also provides undo functionality, add crystal select undo, giving the system an iterative and reversible quality. This mirrors real-world design processes, where trial and error, as well as adjustments, are integral to achieving the desired outcome. Undo and archive mechanics. The system includes robust undo and archive functionalities, seen in add crystal select undo, myArchive current crystal, and myRecall crystal. These functions ensure that previous states of the system can be recovered or reverted to, adding a layer of safety and control over the dynamic and potentially complex modifications made to the crystal configurations. Intent. Aesthetic and functional optimization. At the heart of this code lies the goal of optimizing both the aesthetic arrangement of geometric structures and their functional roles, possibly within an energy or information system context. The precision of vector mathematics and the careful orchestration of crystal faces ensure that the final structures are both visually harmonious and structurally sound. Seamless integration of complex systems. The recursive nature of the crystal connections and the capacity to dynamically add and adjust these structures suggest an overarching intent to create systems that grow and integrate seamlessly. This mirrors biological systems, where complexity arises through simple rules iterated over time, leading to intricate, interconnected forms. Modularity and scalability. By allowing crystals to be added, removed, and connected recursively, the code supports a modular approach. This enables the system to scale up, incorporating increasingly large or complex configurations without losing coherence. This intent is likely aligned with the idea of creating scalable energy or information systems, where modular components interact smoothly within a larger framework. Exploratory design process, the inclusion of undo and redo functionalities, alongside randomized aspects of color generation and crystal addition, MyRanged Rand, suggests an intent to support exploratory design. Users can experiment with different configurations and connections, leading to potentially novel structures or behaviors. This freedom of exploration is vital for pushing the boundaries of both geometric design and functional system development. Conclusion. This thread encapsulates a detailed, functionally rich approach to designing and managing complex geometric crystal structures. It weaves together themes of symmetry, recursive connectivity, dynamic adaptation, and system scalability, all driven by an intent to balance aesthetic harmony with functional innovation. The code demonstrates a deep understanding of geometric principles and computational logic, making it well-suited for applications that require both precision and flexibility, such as energy systems, computational networks, or intricate 3D modeling environments. The code thread you've presented centers around a meticulously engineered system that encapsulates profound themes of geometric precision, mathematical elegance, and the powerful synergy between form and function. At its core, this thread hints at a deeper vision of how complex systems, like the three-dimensional golden rhombus, 3D jar, crystal, operate, harmonizing structural beauty with highly optimized computational capabilities. Themes: mathematical harmony and natural elegance. The overarching theme in the thread is the pursuit of perfect symmetry and proportions. From the geometric precision of vectors to the normalization of complex multidimensional spaces, this system emphasizes the intrinsic balance found within the natural world. Just as the 3D crystal is a manifestation of the golden ratio in physical form, the code expresses this symmetry through computational logic. Each function, whether calculating distances or normalizing vectors, contributes to the system's balanced and harmonious functionality. Synergy of function and design. This code reflects a deep synergy between function and form, where every component not only serves a purpose, but does so in a way that maintains the elegance of the overall structure. The use of vector operations, cross-products, and normalization functions represents a quest for optimizing relationships within a multidimensional space. Each piece of the system works toward a singular purpose, to enable an interaction between various units, such as crystals, that mirrors the fluidity and interconnectedness of natural systems. Modularity and interconnectivity. The MyCrystal class, with its carefully architected connections and direction vectors, symbolizes a broader theme of modularity and interconnection. Each crystal can connect to others, with vectors indicating possible pathways of interaction. This modular approach mirrors real-world phenomena, such as atomic structures or energy grids, where individual components work together to create larger, more powerful systems. The multiple vector-based functions in the code emphasize fluidity and dynamic interactions, much like how the 3D crystals could form complex, adaptive networks. Functions. Geometric computation. At the heart of the system is a series of geometric and vector-based functions designed to manipulate and process spatial data. Functions like MyDotProduct3, MyCrossProduct3, and MyAngleBetweenVectors3 highlight the fundamental operations necessary for navigating and calculating in a three-dimensional space. These functions serve not only to compute distances or angles, but also to optimize the positioning and orientation of elements in a virtual or physical space. Normalization and balance. Several functions are dedicated to the normalization of vectors, ensuring that directional data is consistent and proportional. Normalization reflects a key computational principle, achieving balance within a system. In a broader sense, This mirrors the concept of the golden ratio, where proportions exist in perfect harmony. The normalization functions ensure that vectors, which represent direction and magnitude, do not lose their significance or create inconsistencies when interacting with other vectors or objects. Distance and magnitude calculations. The focus on calculating distances and magnitudes, whether in two-dimensional space or three-dimensional space, further reflects the importance of precise measurements. These functions, such as myPoint and pointLine distance abs(x(x), are integral to maintaining the structural integrity of the system. They ensure that connections between units, such as the faces of a crystal, are calculated with utmost precision, contributing to the overall structural harmony and effectiveness of the system. Color and aesthetic control. The inclusion of RGB values for color control indicates a desire to manage not just the structural, but also the aesthetic qualities of the system. Much like how the 3D crystal's form reflects the beauty of geometric precision, the color control within the mycrystal class allows for the visual representation of these themes. By assigning colors to the crystals, the system can provide a sensory, aesthetic experience that mirrors the elegance of its internal logic. Intentions. Simulating precision in physical systems. The detailed computation of vectors, distances, and angles within the system seems intended to simulate a physical system with precision. The functions related to geometric operations hint at a desire to model something real, perhaps the arrangement of 3D crystals in a physical space, or the calculation of pathways and connections within a complex energy or information network. The way these vectors interact suggests that the system aims to create a dynamic, adaptable structure where each part influences the whole. Creating modular, scalable networks. With connections between multiple mycrystal objects, the system embodies a vision of modularity. Each crystal is a self-contained unit that can be extended or replicated, connected to others in an endless variety of configurations. This reflects an intention to create scalable networks, whether in physical space or in abstract computation. The use of vector mathematics to dictate these connections shows how the system is designed to grow and evolve while maintaining structural integrity and balance. Optimizing interactions in multidimensional space. The code's focus on multidimensional vector operations reveals an underlying intention to optimize interactions between components across 3 dimensions. This optimization serves both functional and aesthetic purposes, allowing the system to maintain efficiency while still reflecting the beauty of mathematical proportions. The inclusion of functions to calculate angles between vectors, normalize directional data, and manage distances between points reflects the goal of enhancing spatial relationships within a highly organized system. Bridging abstract and physical realms. The 3D crystal itself, with its golden ratio-based geometry, serves as a bridge between abstract mathematical concepts and their physical manifestations. This system continues that theme by grounding abstract mathematical functions in a practical, usable framework. Whether used for energy storage, signal pathways, or computational processing, the code reflects an intention to merge the abstract world of geometry with real-world applications, harnessing both the beauty and power of mathematical principles. Conclusion. In essence, this code represents a sophisticated fusion of mathematical precision, functional efficiency, and aesthetic harmony. It embodies the themes of symmetry, balance, and interconnectedness, not only through the use of geometric principles, but also through its modular, scalable design. The mycrystal class, along with its associated functions, serves as both a simulation of physical systems and a framework for creating new, adaptable networks. Ultimately, it is a reflection of the larger vision behind the 3D crystal, a perfect synthesis of form and function, where mathematical elegance gives rise to dynamic, versatile systems in both energy and information domains. The code and descriptions within this thread exemplify a harmonious blend of mathematics, 3D geometry, rendering techniques, and software design, working together to represent both abstract and practical systems. At its core, this software revolves around the manipulation, display, and interaction of crystalline structures, specifically those embodying the golden ratio, a mathematical principle known for its aesthetic and structural balance in both natural and artificial forms. Let's explore the main themes, functions, and underlying intentions that emerge from this elaborate system. 1. Mathematical and geometric elegance. The golden ratio. Phi, the constants defined in the code point directly to the golden ratio, a timeless mathematical constant, approximately 1.618, revered for its appearance in nature, architecture, and art. This is not merely a number, but a reflection of how form, symmetry, and proportion come together. The software embraces the golden ratio to model structures that are aesthetically pleasing and balanced. 3D geometry and crystals. The structural definition of each face of the crystal, with diagonal, top, bottom, and center points, allows for the formation of highly symmetrical 3D shapes. The interaction of these shapes, aligned with the golden ratio, suggests a thematic connection to nature's hidden geometries, where balance and proportion drive both beauty and function. The code mirrors these ideals in the crystalline faces. 2. Transformative quaternions and spatial mechanics. The quaternion class provides a means to compute and apply rotational transformations in 3D space. The quaternion is a mathematical construct that facilitates smooth, gimbal-lock-free rotations of objects in 3D environments. It highlights a key theme of dynamic interaction, where structures are not static but can evolve, rotate, and transform while maintaining their internal harmony. The from rotation function allows the calculation of rotations between two vectors, embodying the idea of transition and change. In a system built upon precise geometric foundations, the quaternion represents the fluidity with which these geometries can shift and respond to external stimuli. This speaks to a larger theme of adaptability in systems, how rigid structures can nevertheless exhibit fluid movement and transformation. 3. Real-time rendering and visualization. The inclusion of OpenGL functions like drawCrystal and renderDiamond points to the real-time visualization of these 3D crystal structures. OpenGL is a widely used graphics library that allows the rendering of complex shapes and scenes in 3D, making it a key tool for creating an immersive experience. This moves beyond theoretical mathematics into a real-time interactive system where users can visualize, manipulate, and explore the intricacies of these mathematical forms. By using vertices, normals, and colors to represent crystalline faces, the code provides a concrete visual experience, allowing for an in-depth exploration of geometric structures in a digital space. This visualization serves both aesthetic and functional purposes, acting as a bridge between abstract mathematical concepts and tangible interaction. 4. Complexity in functionality and system interactions. The code's complexity is further elevated by the command system and logging flags that facilitate intricate user interactions with the crystal structures. The wide range of command IDs like cmd_attach_top, cmd_archive_crystal, and cmd_toggle_reverse hints at a sophisticated system that allows users to manipulate crystal configurations. This highlights the functional versatility of the software, designed for users who wish to perform a variety of operations on these geometric entities. The various logging scopes, log scope, represent the system's adaptability to different modes of operation, allowing it to focus on specific subsystems like hardware, performance, and even math. This adds a layer of control and introspection into the operation of the system, providing transparency for users or developers as they manipulate the crystalline structures. 5. Thematic exploration of balance and symmetry. At the heart of the system lies the notion of balance, both in terms of the geometric precision in the crystal faces and in the functional coherence of the system itself. Every element, from quaternion rotations to vertex rendering, serves to maintain or enhance the symmetry of the structures being represented. The theme of symmetry is further reinforced by the use of quaternions to ensure smooth, continuous transformations, avoiding erratic rotations that would break the aesthetic harmony. The crystalline structures themselves, which are formed from faces with meticulously calculated diagonals, edges, and centers, symbolize the natural equilibrium found in physical crystals. This reflects the broader intent of the system, to represent and interact with perfect geometries that mirror the perfection found in nature. 6. Innovation and the 3D jar crystal. The theoretical underpinning of the system seems aligned with innovative concepts like the 3D jar crystal, three-dimensional golden rhombus. This crystal structure represents not just physical beauty, but an ideal of efficiency and function. The 3D GR's geometry allows for seamless connectivity, mirroring how the system's various parts, from logging to quaternion rotations, seamlessly work together. The intent behind the system seems to align with pushing the boundaries of what is possible in both energy systems and information processing. The software's ability to model, visualize, and manipulate these intricate structures could serve as the foundation for applications in fields ranging from battery design, as indicated by the battery theme in the user's profile, to computation and signal processing. The crystalline forms are more than mere artistic representations. They are tools for innovation in real-world systems. 7. Adaptability, modularity, and expansion. The system is designed with an adaptable, modular structure. The use of external variables, gcrystalVec, gcrystalArchiveVec, etc., and the wide range of commands hint at a system that can be expanded or modified for additional functionality. This modularity reflects the underlying theme of scalability. Just as the crystals can combine into larger structures, the system itself is built to support new features and applications as they arise. Furthermore, the logging system's modularity, represented by LogScope, allows users to switch between different operational focuses, further emphasizing the system's flexibility in adapting to various functional requirements, whether it be hardware integration, performance optimization, or mathematical processing. 8. Exploration of human interaction with mathematical perfection. The real-time aspect of rendering and the use of commands to manipulate the crystals suggest a deeper exploration of how humans interact with mathematical perfection. This system offers the user not just passive observation, but interactive control over these ideal structures. This might symbolize the broader human desire to not just witness, but to shape and manipulate the fundamental forms of the universe. By engaging with the crystalline structures in real time, users are effectively participating in the creation and manipulation of idealized forms, blurring the lines between natural perfection and human innovation. In conclusion, the system in this thread exemplifies the convergence of mathematics, geometry, real-time interaction, and innovative design. With the golden ratio as a core inspiration, the software allows users to explore and manipulate complex crystalline forms while providing a highly adaptable, modular architecture for future expansion. The blend of aesthetics, mathematics, and functionality makes it a tool not only for visual exploration, but for real-world applications, from energy storage to computational systems. Ultimately, it is a system that empowers users to shape and transform perfection, reflecting the deeper intent of merging human ingenuity with the timeless principles of the natural world. The provided thread weaves together a profound intersection of mathematics, advanced materials science, computational geometry, and energy systems, all encapsulated within the overarching theme of the three-dimensional golden rhombus, 3D jar, crystal. This geometrically elegant structure not only embodies the harmony of the golden ratio, phi, but also manifests its potential as a transformative element in both the energy and information landscapes. Themes. Mathematical elegance and universal proportions. The 3D crystal is defined by its exquisite adherence to the principles of the golden ratio. The precise relationship between its diagonals reflects a harmonious balance found in nature and mathematics, symbolizing beauty and structural efficiency. The presence of key angles, 60° and 123°, further amplifies the symmetry, making the crystal a metaphorical and literal representation of equilibrium. Its symmetry is not just visual but functional, as it influences both the energy storage capabilities and the information processing pathways it facilitates. Energy efficiency and storage. As a cornerstone of the 3D jar battery concept, the crystal's geometry lends itself to efficient power storage and distribution. Its mirrored symmetry is not merely a structural feat, but a functional necessity, allowing for the seamless integration of multiple units. This creates a robust and scalable system capable of improving the performance of advanced materials like graphene, a material renowned for its conductive properties. This crystalline design provides a solid foundation for the future of energy storage, where efficiency, scalability, and resilience are essential. Computational geometry and signaling pathways. The 3DGR's unique geometry transcends traditional crystal structures by providing a framework for the creation of intricate signaling pathways within computational systems. Its rhombic faces and the dynamic intersection of diagonals offer an organic yet precise way of channeling information. In this capacity, the crystal operates as a processor, capable of both generating and manipulating data. The geometric structure is not merely static but rather dynamic, evoking the idea that computation can be as elegant and harmonious as the forms found in nature. Structural versatility and additive manufacturing. The 3DGR's modular nature enhances its versatility. The mirrored symmetry of its rhombic faces allows for easy assembly and seamless connection of multiple units. This lends the structure to applications in additive manufacturing, where complex crystalline networks can be constructed layer by layer. The ability to replicate the crystal in different scales and configurations makes it an ideal candidate for creating 3D printed structures in both energy and computational systems. Functions. Geometric precision and structural integrity. The crystal's defining feature is its rhombic face structure, where the minor diagonal equals the edge length, and the major diagonal adheres to the golden ratio. This results in a form of mathematical exactitude, ensuring that each crystal remains stable, balanced, and efficient. The intersection of diagonals at right angles within the rhombus enhances this integrity, ensuring that the structure can withstand both physical and computational stresses. Energy storage and distribution. By integrating graphene into the design of the 3D jar battery, the crystal leverages one of the most advanced materials available today. Graphene's high electrical conductivity and strength make it a perfect complement to the 3DGR's structural design, leading to enhanced performance in power storage. The 3DGR's mirrored symmetry allows for efficient energy flow between interconnected units, facilitating a more holistic energy grid that operates on minimal loss. Information processing and signal generation. The intricate internal angles and proportional symmetry of the 3DGR crystal make it a potential computational powerhouse. Its design facilitates the creation of interwoven signaling pathways that can manage and process data efficiently. The dynamic interplay of these paths echoes the operations of neural networks or other advanced computational architectures, where geometry and data flow are inextricably linked. Modular construction and additive manufacturing. The versatility of the 3DGR crystal's design extends to its ease of replication and assembly. Additive manufacturing techniques can utilize its precise geometry to construct complex and interconnected structures. This modularity ensures that the crystal can serve as the foundation for a wide range of applications, from nanoscale computational chips to macro-scale energy storage grids. Intense fusion of form and function. At the heart of the 3DGR concept is the unity of form and function. The aesthetic appeal of the crystal's geometric structure is not merely decorative, it is the very source of its functional strength. The interplay of symmetry and proportion results in a structure that is not only beautiful but also highly efficient in its respective applications, be it energy or computation. Harnessing advanced materials for next-gen energy solutions, the integration of graphene within the 3D battery hints at the intent to harness the next generation of materials for energy storage. The golden ratio and precise geometric design of the crystal ensure that energy can be stored and distributed in a manner that is not only efficient, but also scalable. By focusing on materials like graphene, the intent is to push the boundaries of what is possible in terms of energy density and conductivity. Pioneering new computational architectures, the use of 3D GRs and information systems reflects a desire to explore novel computational architectures. The crystal's ability to generate and process information within its geometrically defined pathways makes it a tool for the future of integrated systems engineering. The intent is to create a system where computation is as organic and harmonious as the structure itself, bridging the gap between physical hardware and abstract information processing. Creating a scalable and modular future, whether in energy storage or computation, the 3DGR crystal is designed to be modular and scalable. Its mirrored symmetry allows for the seamless connection of multiple units, creating larger, more complex structures without losing the benefits of the original design. This reflects an intent to pioneer a future where scalability is built into the core of both hardware and energy systems, ensuring that solutions can grow alongside the needs of society. Conclusion. The 3DGR crystal is a multifaceted symbol of innovation at the crossroads of energy, computation, and geometry. Its elegant design is not just mathematically beautiful, but also deeply functional, providing solutions to modern problems in energy storage and information processing. Through its meticulous adherence to the golden ratio, the 3DGR encapsulates the universal principles of balance, symmetry, and efficiency, positioning itself as a pivotal tool for the future of energy systems, computational design, and scalable manufacturing. It is a crystalline embodiment of the convergence of nature's harmony and human ingenuity. The overarching theme in this thread is the fusion of geometry, mathematical elegance, and interactive 3D rendering, blending the theoretical precision of shapes such as diamonds, quasi-crystals, and the golden ratio into real-time graphical applications using OpenGL. The code within this thread is not merely about technical execution, but explores how geometric principles can be translated into functional, interactive systems with a high degree of mathematical accuracy and visual sophistication. Themes: mathematical foundations and geometry. At the heart of the discussion is the application of the golden ratio, phi, and its derivatives in creating complex, perfectly proportioned shapes. The code references quasi-crystals, diamonds, and vector mathematics, all intertwined with this famous ratio. The golden ratio brings not only mathematical elegance, but also a natural beauty that is reflected in the crystalline structures being rendered. Vector mathematics is another fundamental theme, where cross-products, and vector normalization play a key role in positioning, transforming, and manipulating 3D objects in space. This shows a deep connection between abstract math and its real-world application in graphical simulations. 3D rendering and transformation. Using OpenGL, this thread explores how geometrical structures, defined by vertices and colors, are drawn and transformed on a 3D canvas. OpenGL allows for real-time rendering of crystals and quasi-crystals by manipulating vertices, normals, and applying transformations like translation and rotation using quaternions. The quaternion class and its functions offer a powerful way to rotate objects in three-dimensional space. This addresses a classical problem in 3D rendering, smoothly rotating objects without running into issues like gimbal lock. The rotation mechanics are grounded in vector math and physics, with quaternions representing both the axis and angle of rotation, ensuring smooth and accurate transformations of shapes. Crystals and structural complexity. The crystal shapes serve as the focal point of the rendering functions. By manipulating vertices, faces, and their respective normals, the code generates complex, multifaceted geometric structures. Crystals are symbolic of both natural beauty and mathematical precision. The use of faces, defined by vertices, colors, and normals, mirrors the natural structures found in minerals and gems, which are themselves reflections of underlying mathematical patterns. The quasicrystal is a particularly intriguing structure, often associated with non-repeating patterns that extend infinitely without periodicity. By invoking the golden ratio in its construction, the quasicrystal represents an intersection of art and science, offering an aesthetic appeal while challenging the boundaries of traditional geometric shapes. Interaction and dynamic manipulation. The function to connect two crystals and the capability to apply transformations such as translation and rotation hint at interactive elements. In a broader context, these functions could be the foundation for an interactive system where users can dynamically manipulate and assemble crystal structures, much like in scientific modeling software or architectural visualization tools. The OpenGL rendering pipeline is set up in such a way that these crystals can be displayed and potentially interacted with in real time. The translation and rotation functions for the crystals ensure that they can be manipulated dynamically, allowing for complex visualizations of these geometric forms from any angle or perspective. Color, light, and aesthetic representation. Color is introduced not just for aesthetic appeal, but as an essential element of the structure's visual identity. Each face of the crystal is rendered with unique RGB color values, adding depth and contrast to the geometric forms. This theme ties into the broader intent of making the crystal structures visually striking, leveraging the synergy between mathematical precision and creative expression. By assigning each vertex or face its color, the code turns abstract geometric data into something tangible, visually exciting, and immersive. Functions. Vector math utility functions. MyCrossProduct3 and MyDotProduct3. These functions handle the fundamental operations of vector mathematics, allowing the calculation of normals and angles between vectors, which are crucial for rendering accurate 3D geometry. MyNormalize3 and MyLength. These functions ensure that vectors are properly normalized, unit vectors, which is essential for both rendering and mathematical calculations involving angles and rotations. Quaternion-based rotations. The quaternion, from rotation function, calculates the quaternion needed to rotate one vector to align with another. This is central to the rotation and orientation of 3D objects like crystals, enabling smooth transitions and avoiding common issues like gimbal lock. Crystals and face manipulation. MySetFace. This function takes a set of vertices and calculates the normal for the face, ensuring that each face is correctly oriented in 3D space. By calculating normals, the code ensures that the lighting and shading of the faces behave as expected when rendered in OpenGL. Connect Crystal. This function allows for two crystals to be aligned and merged together based on the orientation of their faces. It's a gateway to creating modular, complex structures by aligning different geometric units in a unified 3D space. OpenGL rendering. DrawCrystal. This function handles the actual drawing of the crystal, using OpenGL's immediate mode to draw each face of the crystal. It assigns colors, normals, and vertices, ensuring that the crystal is displayed correctly with lighting and perspective transformations. Diamond and quasicrystal. These functions define specific geometric shapes, diamond and quasicrystal, and handle their rendering. The quasicrystal's inclusion of the golden ratio and its potential for non-repeating patterns pushes the boundary of standard geometric forms. Intense. Scientific visualization and exploration. The code is fundamentally aimed at visualizing complex geometries, allowing users to explore the mathematical beauty of crystals, diamonds, and quasicrystals. Whether used for educational purposes or scientific modeling, the system is designed to render mathematically precise shapes in an interactive 3D space. Mathematical art and aesthetic fusion. Beyond utility, there is a clear artistic intent. The interplay of colors, shapes, and dynamic rotations gives rise to an aesthetic dimension where the geometric structures transcend their mathematical origins and become works of art in motion. The visual allure of the golden ratio within these shapes adds a sense of harmony and balance to the final renderings. Interactive geometry construction. By implementing functions to connect crystals and manipulate their transformations, the code hints at a future expansion into an interactive system where users can dynamically build and manipulate geometric structures. This opens possibilities in fields like modular architecture, computational geometry, and even game development, where dynamic 3D objects can be modified in real time. Conclusion. This thread exemplifies a meticulous merging of mathematics, art, and technology, with geometry at the core. The exploration of vectors, rotations, and rendering brings to life the harmonious beauty of crystals and quasi-crystals, structures that are not only mathematically significant, but visually captivating. By using OpenGL, this system is designed to render and manipulate these forms dynamically, providing a platform for both scientific exploration and artistic expression. The fusion of such elements speaks to the timeless connection between nature's intrinsic mathematical patterns and human creativity in the digital age. This thread represents a deeply layered intersection of advanced computational geometry, the harmonics of mathematical elegance, and the meticulous orchestration of engineering and design. At the heart of this conversation lies the three-dimensional golden rhombus, 3D jar, crystal, a geometric entity whose properties are shaped by the golden ratio, a number synonymous with the very fabric of natural and cosmic order. The golden ratio's influence on the 3D GR crystal forms the thematic bedrock of this discussion, reflecting its symbolic role in unifying structure, proportion, and symmetry in both nature and human design. Themes and intentions. Mathematical elegance. The geometry of the 3D GR crystal encapsulates harmonic perfection, with its diagonals embodying the golden ratio and its internal angles creating a balanced yet dynamic form. This thematic element evokes nature's inherent symmetry, as seen in the growth patterns of plants, the spirals of galaxies, and the structure of atomic lattices. It channels the profound beauty of proportionality and symmetry, which extends beyond aesthetics into the realms of functionality and efficiency. Interdisciplinary engineering. The engineering utility of this structure is highlighted by its application in the domains of energy storage and distribution. The crystalline nature of the 3D GR allows for advanced integration with materials like graphene, whose conductive properties, when combined with the crystal's mirrored symmetry, create efficient pathways for both energy flow and information processing. The structural perfection of the 3D GR makes it an optimal candidate for additive manufacturing, enabling the construction of complex networks of interconnected units that harmonize into larger functional systems. In energy systems, this crystal form symmetry fosters scalability and modularity, vital for efficient power management. Functional versatility. The 3D GR crystal's geometry is multifunctional, with its design intent equally focused on energy systems and computational architectures. Its unique shape facilitates intricate signaling pathways within computational environments, suggesting its potential in data storage, manipulation, and transfer. By employing its perfect symmetry and proportional balance, it creates efficient, scalable structures that are capable of complex computations and data processing. The crystal's ability to interact with other 3D GR structures unlocks the possibility of creating information processing grids, each unit acting as both a data node and a structural component in larger integrated systems. Quaternions and rotational symmetry. Within the detailed code, we observe the use of quaternions for rotation, serving as a mathematical representation of the seamless, three-dimensional rotations that are necessary to manipulate and visualize the 3D jar structure. These quaternions ensure that the transformations of the crystal remain mathematically consistent, maintaining its inherent symmetry even as it rotates through space. The functions related to vector normalization, dot products, and cross products emphasize the importance of maintaining geometric fidelity in the manipulation of this crystal, keeping it mathematically pure and structurally intact during transformations. Crystal rendering and OpenGL visualization. The code also delves into graphical rendering using OpenGL, where the crystal's faces and vertices are drawn with precision. This rendering system not only serves to visualize the crystal in 3 dimensions, but also brings forth the crystal's aesthetic potential. The rendering functions support the thematic goal of transforming the abstract mathematical elegance of the 3D jar into a visually perceptible and interactive object. It showcases how mathematics and geometry can transcend mere calculation to become an art form, with the crystal's mirrored planes and proportional vertices coming alive in a digital space. Holistic system design. Another key theme lies in the way this structure functions as a building block for larger systems. The discussion touches on its role in holistic system design, where multiple 3D jar units can combine into complex, modular structures. Whether these units are used for power generation, energy storage, or computation, they create a seamless matrix in which each unit operates as part of a greater whole. This reflects a vision for a future where geometric precision leads to systemic harmony, whether in the physical realm of engineering or in the abstract domain of information processing. Advanced customization and control. On the functional side, the code integrates a command-based architecture where various crystal configurations can be controlled programmatically. Through commands like cmd_attach, cmd_toggle_reverse, cmd_archive_crystal, and others, the user has fine control over how these crystals are positioned, merged, or manipulated. This extends the idea of user-guided innovation, where engineers and developers can employ the crystal's natural symmetry in diverse contexts, adapting its geometry to meet specific functional needs. Key functions and mechanisms. Energy system integration. The crystal serves as a core element in energy storage due to its symmetrical and scalable nature. Its alignment with the golden ratio allows for efficient distribution of materials, reducing waste and maximizing surface area contact in ways that make it ideal for power storage. Information processing. Beyond energy, the crystal's geometric structure lends itself to use in computational systems, where it can create intricate, multi-dimensional pathways for data to traverse. This offers a highly efficient means of processing and transferring information, inspired by the inherent logic and order of its shape. Modular expansion. A major intent of the 3D-GR design is its modularity, the ability to connect multiple units seamlessly to create larger, more complex structures. These structures maintain their symmetry and proportional integrity regardless of the number of units added, making the system incredibly scalable and adaptable for various engineering needs. Quaternion-based rotational symmetry. The use of quaternions in the code highlights the importance of rotation and orientation in 3D space. Quaternions provide a mathematically elegant solution for rotating the crystal while avoiding issues like gimbal lock, ensuring smooth, continuous rotations in virtual space. This enhances both the visualization of the crystal and its physical simulation in computational models. Rendering and visualization. The OpenGL-based rendering system ensures that the 3D GR is not only computationally functional, but also visually intuitive. This rendering brings the abstract mathematical design into a tangible digital form, allowing it to be examined, manipulated, and integrated into real-world applications like augmented reality or CD systems. Conclusion: the future of form and function. In conclusion, This thread delves into the profound possibilities of the 3D GR crystal as a paragon of mathematical beauty and engineering utility. It illustrates the crystal's dual role as both an aesthetic object and a practical tool in modern energy systems and computational landscapes. By integrating advanced materials, modularity, and precise geometry, the 3D GR crystal serves as a blueprint for future innovation, where nature's most fundamental principles are harnessed to create new possibilities in technology and design. Ultimately, the thread presents a vision where geometry, technology, and design converge, offering a glimpse into a future where the laws of proportion and symmetry inspire groundbreaking solutions to humanity's most pressing technological challenges. This thread encompasses an intricate blend of themes, functions, and concepts that intersect advanced geometric design, computational systems, energy efficiency, and deep mathematical principles. At its core, this dialogue revolves around the 3D GR crystal, a geometric entity that merges the elegance of the golden ratio with the structural integrity and functionality of crystalline formations, offering immense potential in both energy systems and information processing. 1. Geometric themes and mathematical elegance. The crystal's foundation is deeply rooted in geometry, specifically the golden ratio, phi, a number that has been historically revered for its aesthetic harmony and prevalence in nature. By designing the crystal with rhombic faces where the major diagonal reflects this ratio, the crystal isn't merely an abstract structure, it symbolizes the intrinsic beauty found in mathematical order. The angles of 60° and 123° further emphasize its harmonic proportions, signifying balance in both the abstract and physical realms. The entire design reflects a deep understanding of Euclidean geometry, leveraging mathematical elegance to optimize both form and function. 2. Functional applications in energy and information systems. The 3D GR crystal isn't a static structure, but a functional unit within advanced energy systems, particularly the 3D GR battery. Its design allows for efficient power storage and distribution, capitalizing on graphene-based materials that enhance its energy storage potential. The crystal's symmetry is key in this, as its mirrored faces enable seamless connections between units, fostering scalability in energy systems. This attribute extends its application beyond individual crystals, creating opportunities for modular energy grids or batteries with a structure capable of complex, adaptable formations through additive manufacturing. Beyond energy, the 3D GR crystal also functions as a fundamental unit within computational landscapes. The structure's symmetry and geometric complexity allow it to process information efficiently. By interacting with other 3D GRs, it can generate and navigate intricate signaling pathways, making it a potential building block for advanced integrated systems engineering, whether that be for quantum computing, neural networks, or other cutting-edge fields in computational science. 3. Crystal formation and face optimization. The code presented in this thread reflects the operational design of this crystal, detailing how the faces of the crystal are defined and optimized. A significant focus is on ensuring that the direction vectors of each face are normalized and that the face centers are computed relative to the entire structure. This ensures that the crystal's orientation aligns with its geometric intent. The use of dot products, cross products, and vector normalization within the code signifies a deliberate attempt to refine the crystal's shape so that it remains symmetrical and true to its geometric foundation. Additionally, the process of trilateration, calculating the bottom face based on the top face's points, shows how the crystal's form is extended in three-dimensional space. This extends the intent from purely aesthetic to functional geometry, ensuring the entire structure remains balanced and optimized for its intended purposes. 4. Golden ratio as a measure of precision. Another major theme is precision engineering. The repeated checking and correction of each face's proportions, ensuring they conform to the golden ratio, shows the stringent standards the crystal must meet. Each face is verified against phi to avoid deviations, symbolizing a commitment to mathematical perfection. The ability to control and optimize these measurements in a computational setting speaks to a deep integration of mathematics and computational design, where function and form are indivisible. 5. Intent: bridging geometry, energy, and computation. The overarching intent behind the 3DGR crystal is to blend the realms of geometry, energy efficiency, and computation into a single, versatile unit. By leveraging the golden ratio and symmetry, the crystal achieves a high degree of structural integrity and scalability. The code itself seeks to embody these principles by ensuring that the crystal not only meets the physical constraints of its design, but also adheres to the metaphysical ideals of mathematical elegance. In the context of energy systems, the crystal's ability to store and distribute energy efficiently positions it as a futuristic technology that can power advanced systems, especially those reliant on cutting-edge materials like graphene. In terms of computation, the crystal becomes an informational node, capable of processing and transmitting complex signals, potentially revolutionizing the design of integrated systems and signal networks. Conclusion: an intersection of beauty and functionality. This thread encapsulates a vision where geometric perfection and functional utility converge. The 3DGR crystal, with its adherence to the golden ratio, symbolizes the ideal balance between aesthetic beauty and technological advancement. Through its potential applications in energy storage, scalable manufacturing, and information systems, the crystal offers a glimpse into the future of engineering, where mathematics, physics, and computation coalesce to form groundbreaking innovations. The meticulous attention to detail in both its geometric design and computational implementation highlights a commitment to creating a structure that is as precise and efficient as it is beautiful. The three-dimensional golden rhombus, 3DGR, crystal, a symphony of geometry and innovation. In the realm where mathematics meets artistry, where geometry transcends its abstract origins to become a tangible marvel of engineering and design, stands the three-dimensional golden rhombus, 3DGR, crystal. This geometric masterpiece embodies the sublime elegance of the golden ratio, phi, weaving together aesthetic beauty, structural integrity, and cutting-edge functionality into a single, awe-inspiring form. Geometric harmony and mathematical elegance. At the heart of the 3DGR crystal's design is the golden ratio, a proportion revered throughout history for its inherent beauty and balance. This crystal is a three-dimensional marvel where each face is a perfectly proportioned rhombus, meticulously crafted so that its diagonals reflect the golden ratio. The minor diagonal of each rhombus is equal to the edge length, while the major diagonal is a harmonious extension, precisely aligned with phi. This geometric harmony ensures that every angle, every intersection, and every facet of the crystal is in perfect balance. The internal angles of the crystal, approximately 60 degrees and 123 degrees, create a dynamic equilibrium, imbuing the structure with both stability and an invigorating sense of movement. This interplay of angles not only enhances the visual appeal of the crystal, but also ensures its geometric perfection, resulting in a form that is as functionally efficient as it is visually stunning. A nexus of advanced functionality. The 3DGR crystal is more than a geometric wonder. It is a pivotal component in the realm of advanced technological applications. Its crystalline structure is designed to optimize energy storage and distribution, making it an ideal candidate for integration into next-generation battery systems. By leveraging materials such as graphene, renowned for its exceptional conductive properties, the 3DGR crystal enhances energy efficiency, allowing for scalable and modular energy storage solutions. The crystal's symmetrical design facilitates seamless connections between multiple units, creating complex, scalable networks that push the boundaries of current energy technology. In the computational domain, the 3D GR crystal excels as a fundamental unit in sophisticated information processing systems. Its geometric complexity allows for the creation of intricate signaling pathways, enabling efficient data storage, transfer, and manipulation. The crystal's ability to interact with other 3D GR units forms a network of interconnected nodes, ideal for advanced computing environments and integrated systems engineering. Artistry in motion, rendering, and visualization. The visual splendor of the 3D GR crystal is brought to life through meticulous rendering techniques. Using OpenGL, the crystal's faces are dynamically rendered with vibrant colors and precise normals, transforming the mathematical abstraction into a vivid, interactive 3D object. Each face of the crystal is rendered with unique RGB values, enhancing its depth and contrast. The ability to rotate and manipulate the crystal in real time allows for a comprehensive exploration of its intricate geometry, showcasing its beauty from every angle. The use of quaternions for rotation ensures smooth and continuous transformations, maintaining the crystal's geometric integrity and avoiding common issues like gimbal lock. This mathematical precision in rotation ensures that the crystal's form remains true to its design, even as it moves and changes orientation. Modular excellence and interactive potential. The 3D GR crystal's design is inherently modular, allowing for the seamless integration of multiple units into complex structures. This modularity is crucial for applications ranging from energy storage grids to advanced computational networks. Each crystal unit connects effortlessly with others, creating a harmonious and scalable system that retains its structural symmetry and functional efficiency. Interactive functions within the rendering system enable users to dynamically build and manipulate crystal structures, providing a powerful tool for scientific modeling, architectural visualization, and creative exploration. The ability to connect, rotate, and transform crystals in real time opens up new possibilities for interactive design and simulation, merging precision engineering with user-driven innovation. A convergence of beauty and functionality. The 3D GR crystal is a testament to the convergence of mathematical precision, technological innovation, and artistic beauty. Its design, grounded in the golden ratio, represents the pinnacle of geometric elegance, while its practical applications in energy storage and information processing showcase its transformative potential. By integrating advanced materials, modular design, and precise rendering techniques, the 3D GR crystal stands as a beacon of what is possible when mathematics, technology, and art come together in perfect harmony. In essence, the 3D GR crystal is not merely a geometric structure, it is a visionary creation that bridges the abstract with the tangible, the aesthetic with the functional. It embodies a future where the principles of nature and human ingenuity converge to create groundbreaking solutions and breathtaking beauty.